In the last video, we did some simple Lewis structures for molecules that had only two atoms in them. Two of the ones that we did were the hydrogen molecule, H2, and we also did hydrogen fluoride, HF. We didn't do F2. Do this one yourself. Try and put this one together and see if you get what I'm getting here. Now if I look at these three molecules, they're sharing electrons, and that's what's holding the molecule together. But one of them is not like the others. Here you've got two hydrogens on either end of the bonding pair. And there's a +1 nucleus here and a +1 nucleus here, and they're pulling on those bonding electrons. But they're pulling evenly because you've got the same thing on either end of the bond. So it's like a tug-of-war between these two atoms for the shared electrons. Now, same thing with the fluorine here. You've got atomic number 9 for fluorine, so that means you have a +9 charge on the nucleus. So the nucleus that's here and the nucleus that's here are the same strength, and they're both tugging equally on that bonding pair. But here you've got kind of a big dog and a little dog having a tug-of-war. And this one only has a +1 charge, and this one's got a +9. So those bonding electrons, that bonding pair, is not going to be shared evenly. So in a covalent molecule there is always sharing, but it's not always even sharing. And we'd like some way of being able to tell how evenly shared or unevenly shared the electrons are. Because if they're unevenly shared, that is going to do something kind of important to the molecule. It's going to give it a negative side and a positive side. This molecule is the same on both ends, and so is this one, but this one, it's different on both ends. Because the fluorine has a +9 charge on its nucleus, it's going to draw those bonding electrons towards it, and this end of the molecule will be a little bit negative. So if I draw the bond here, I can show that electrons are being pulled from this positive end towards the negative end. This little arrow I'm going to call a bond dipole. And the arrow has a little cross piece here on the positive end of the bond. Now it is pretty easy for me to tell here who the big dog is because it's the one with a bigger nuclear charge, but a lot of times it isn't easy to tell just from the nuclear charge which atom is going to get the lion's share of the bonding electrons. So I'd like to have some sort of a score that tells me greediness for bonding electrons. And that score is what I call the electronegativity, what everybody calls the electronegativity. Electronegativity tells you how greedy an atom is for bonding electrons. And here we would say, well, the fluorine is more electronegative than hydrogen. It'd be nice if we had some numbers here. And there are numbers. Linus Pauling, who's discussed in your textbook, he won a Nobel Prize in chemistry, but also a Nobel Peace Prize for his other work, set up an electronegativity scale. Let's draw in some of the stuff on his scale. I'm drawing like the top of the periodic table in here. I'm going to leave out the noble gases because they don't form compounds. They don't form bonds, covalent bonds, usually. Sometimes they do. You can make them form covalent bonds in the lab. But I'm not going to put them on my electronegativity scale because that doesn't happen naturally very much. And if I look at these, let's see, if I look at these elements, you've got a table of these in your book of the original Pauling electronegativities. Let me copy them over here so we can look at them. Okay, so we've got an electronegativity of 2.1 for hydrogen, 2.0 for boron, 2.5, 3.0, 3.5. So this is a nice simple pattern that we're seeing here. If we look at, let's put some other ones on here. And these are in your book, so no big deal. Your chlorine is 3.0. Sulfur is 2.5. And phosphorus is 2.1. All right. So those are the Pauling electronegativities for these. What can we do with them? Let's look and see how they tell us that we've got the bond dipole here right. It's 4.0 for fluorine, and it's 2.1 for hydrogen. So the electronegativity difference is like 1.9, right? It's pretty big. That's a huge difference. And the one with the negative end is going to be the higher electronegativity atom. Now let's compare a series of bonds. Let's suppose we have an oxygen-hydrogen bond, an oxygen-carbon bond, and an oxygen-fluorine bond. And we want to see which one is the most polar. That is the one that has the biggest separation. The electronegativity difference is large for more polar, larger for more polar bonds. Alright, if I look at my electronegativities, I can fill them in. It's 3.5 here for oxygen and 2.1 here for this, so that's like 1.4. There's a difference of 1.4 for that bond. And where's the negative end of the bond? It's going to be the oxygen end. So if I was going to write in the little dipole moment, I'd write it in like that. And how about this one? It's 3.5 for oxygen, and what is it for carbon? It's 2.5. So that's got a difference of 1. It's less polar, but still the more electronegative atom is the oxygen, so the bond dipole will point like that. How about this one? Oxygen's 3.5 and fluorine is 4.0, so there's only a 0.5 difference here. So the bond dipole is also going to point away from the oxygen here. So this bond is going to be fundamentally less polar than the other two, and it also points, the bond dipole points in a different direction. It points away from the oxygen. So the oxygen is having its electrons be sucked away by the fluorine here. And the most polar of these bonds is going to be the oxygen-hydrogen bond. Okay, so you should be able to draw a bond dipole in using electronegativity values, and you should be able to, from a list of bonds, be able to judge which one is the most polar. This one is the most polar. Now you can interpret these electronegativity differences in a very rough way. And you can tell the difference between polar and nonpolar bonds like this, obviously. But also covalent and ionic bonds. If you have an electronegativity difference of, I'd say, less than about 0.4. This is kind of arbitrary, right? I'm going to call that pretty much just a covalent bond. It really is not very polar at all. And you can call it a pure covalent bond. If you were a real stickler, though, what you would say is you have to have an electronegativity difference of 0 to have a pure covalent bond. But if you've got something like a carbon-hydrogen bond, they don't consider that very polar. It isn't a very polar bond. If you look at the electronegativity values, there's only a difference of 0.4. So by my scheme here, by your book scheme, I'm following your book scheme, this would be a pure covalent bond. You wouldn't say it was polar. You wouldn't say that the bond dipole, what there was of it, would point towards the carbon, but it's so small you can kind of neglect it and say that it doesn't really matter a lot in real processes. And we do in fact see hydrocarbons, carbon and hydrogen compounds. They're pretty much nonpolar. There aren't little separations of charge in there. Now if I have an ionic molecule, or an ionic compound, I should say, you've got an electronegativity difference of maybe bigger than 1.8 for that. So I'm going to call that ionic. And anything between these two extremes is going to be a polar covalent bond. So you're going to be asked to classify bonds as pure covalent, polar covalent, or ionic. You can do that on the basis of electronegativity differences. Suppose you don't have an electronegativity table in front of you, though. Can you still do this? Sure. Look at the periodic table. All of the high electronegativity elements are cramped up in this corner, and the very low electronegativity ones are down here. If you're going like between, say, sodium and chlorine, there's a tremendous electronegativity difference there. And that's going to make this an ionic compound. But if you've got something closer, like sulfur and chlorine, they're very close on the table, so there's going to be a smaller electronegativity difference. So that's probably going to be more of a covalent. That's definitely not going to be an ionic compound. If you go ahead and look at the electronegativity differences there, it's 2.5 and 3.0, so there's an 0.5 difference in electronegativity, so really it is almost on the verge of being a pure covalent bond, a sulfur and chlorine bond. Almost on the verge of it. Just a little bit polar, with the pole pointing towards the chlorine. So you can get away with just roughly deciding whether you have an ionic bond or a covalent bond that way. An easier way to do it is that rule of thumb that we talked about. It's an ionic bond if you've got a metal and a non-metal. You're usually pretty safe by classifying a bond like that as ionic bonding. And polar covalent bonds are in the gray area between pure covalent bonds, pure sharing, and ionic bonds.